Hello and welcome to our educational webinar on sustainable drainage design. Thank you for taking the time out of your day to join us today. We're going to give you an introduction to sustainable drainage design and some of its concepts today. But first, I'd like to just briefly introduce Innovyze for those of you who've not heard of us before. We have a long history of providing software for design, modelling, management and data analytics in relation to water, wastewater, stormwater and flooding, and the assets associated with water. Our experienced engineering team back up all of our software with excellent customer service, support and training, so you can be sure you're not on your own. I'm Jessica Jefferys and I am a product manager here at Innovyze. I've worked for Innovyze for 12 years in the drainage design sector, helping engineers deliver drainage designs to their clients. I've covered a range of roles including support, training and product management, and I now look after our international drainage design software, XP Drainage, which you'll see a little later. I'd like to draw your attention to the GoToWebinar interface. You can use the questions field at any point throughout the webinar. I'll try and keep an eye on it, answer any questions as we go, but any of those I don't get to, I will pick up at the end and talk through the questions with everybody or contact you individually. If you're looking for a certificate for your attendance today, each person must be registered, even if you're watching as a group. I'll run through how to get your certificates, whether you're watching on your own or as a group, and give you the password on how to obtain those at the end of the webinar. We're going to cover today a few different topics, starting with what is sustainable drainage design, what are we talking about, try and get you through some of the acronyms that exist around this topic, run through some of the design criteria we might want to use when we're designing sustainable drainage, and then spend a bit of time talking about the different types of sustainable drainage, the structures or facilities, before introducing you to the XP Drainage software. I've got a small example site just to run through in the software and show you a bit of the detail of how we can include sustainable drainage in our drainage designs. And then, as I said, come back to the questions at the end of the day. So the acronyms, you may have noticed that sustainable drainage is called a lot of different things depending where you are in the world, and I'm sure this isn't the entire list, but the main ones that are used I've tried to cover here. So you may have seen the term LID or LIDs plural, which stands for low impact development. This originated in the United States and was initially a term used just to describe the approach to development, but with water as a real consideration. So trying to have a lower impact in terms of the excess runoff, in terms of the demand for water, and also over time it's become LIDs and started to refer to the actual facilities themselves, such as this rain garden. GI or green infrastructure, again, is a term that was probably first used in the United States, but is quite common all around the world now, and essentially is a way of describing the things that we put in terms of infrastructure that are greener than perhaps traditional roads, drainage, highway items and so on. Then we have BMP or best management practice. Again, started perhaps as an approach but has become more synonymous with the actual storage structures, BMPs, is often used to refer to the actual sustainable drainage elements themselves, as is SuDS or sustainable drainage systems, which we'll generally use today as the term to refer to items such as rain gardens and swales and so on. Water sensitive urban design is another acronym used, WSUD or WSUD. This one originated in Australia, and again describes the approach taken in terms of trying to be more sensitive to water, particularly in areas in Australia, for example, that suffer from very low rainfall and droughts. But it's equally applicable where we have high rainfall and flooding. If we can be a bit more sensitive about the water, then that's going to result in a better urban design overall. And then we have SCM or stormwater control measures. So this is very much referring to the structures or facilities themselves, and is sometimes even just abbreviated to stormwater controls. I've just had a question pop up from someone to say they can't hear the presentation. Perhaps if anybody else can't, if anybody can hear the presentation, sorry, if they can just ask a question just to let me know that it's all working okay. Thank you. I've got two of you popped up there, so that's great. I'll just answer privately and let the person know. I think it's all sorted. Okay, so moving on with the slides. I wanted to mention one particular resource. There's loads of brilliant resources on sustainable drainage all over the world. All you have to do is use the internet to find them. But there's a resource in the UK called sustrain.org, and it's put together by a research body with representatives from academia to landscape architects to approving authorities to consultants and designers. We're a supporter, as are other software companies, and it has a glossary, it has lots of blogs and fact sheets about sustainable drainage, but it also has a really good selection of case studies. So if you're new to sustainable drainage and you're looking for some examples of how these are being successfully implemented, you can go on here and have a look. So what does a good traditional drainage design look like? Typically with drainage design, we have to have no worsening from our existing scenario. So if we're developing, say, an undeveloped area, some landscape, a field maybe, and putting some housing development on the field, we might need to do some hydrological assessment to see what the runoff is from our field. Whenever we develop, we're generally making the surface behave differently. Typically, if we go from a green field to a housing development, there's going to be some paved areas, there's going to be roofs, and traditionally these would contribute the runoff more quickly and more of it. We wouldn't get as much natural infiltration or evapotranspiration, and there wouldn't be the natural elements that slow down the flow, vegetation and so on. But we still have to have no worsening from the existing scenario. So in a traditional drainage design, that normally means we have to put in pipes and storage to deal with the excess flow, rather than just discharge it off-site and potentially cause some flooding problems downstream. And that might be up to a certain average recurrence interval, which is sometimes referred to as a return period. And the pipes have to deal with the flow, the storage has to deal with the extra volume of water, and we have to release that slowly, normally off-site, so there's no negative effects. And potentially also look at our overland flow paths, what happens when we have a very extreme event, even if we are controlling most of the water underground, we might find there's some exceedance for, say, a 100-year average recurrence interval or return period that is flowing above ground, but we will have to demonstrate that that is contained, for example, within the roadway, that it doesn't affect properties, there's no risk to life, and so on. So these are things we have to do regardless of what type of drainage we're looking at. But with sustainable drainage, we want to consider other benefits as well. So that's very much focused on water quantity, how much water was coming off the site previously, how much extra water is coming off the site now it's developed, and not necessarily considering the wider benefits that a drainage solution can offer. We're having to take a more holistic approach, and whether we call it green infrastructure or sustainable drainage or something else, we want to take account of the more natural surface flows and ground conditions. For example, if we already have some slopes on the site, we're going to have a better approach by considering where the water wants to naturally go, and where it might settle, where it might infiltrate best. For example, if we have different soil types across the site, we're likely to need to have the same conditions with a sustainable drainage approach in terms of pre-development and post-development flows. So we will still need to consider the water quantity benefits, but actually the quality as well as the quantity, and the other benefits drainage can offer. For example, we may be able to add amenity value. Typically, maybe in traditional drainage design, this little inlet in the curb here that you can see would go into a grate, just a metal grate, and go under the road, and be carried in a pipe downstream. Whereas with this type of approach, very small rain garden, we're adding more green into our streets and they become more aesthetically pleasing. The term grey to green is often used in schemes that are trying to improve the aesthetics by putting sustainable drainage in. We may also be able to encourage ecological diversity. Even in something as small as this rain garden, we're going to be supporting some ecology. There's going to be an increase in biodiversity. And if we take this approach across the whole site, then maybe we can go as far as having a wetland and offering much more benefit than just dealing with the water. There's also the potential with sustainable drainage to reduce potable water usage. And as I go through the different types of sustainable drainage systems, I'll talk in a little more detail about some of them that help us to do that. So we want to think about the multiple benefits, as I said, the quantity, the quality, amenity, biodiversity, water reuse, so reducing our potable water, possibly groundwater recharge as well. So we may find that on a natural site pre-development, we're actually getting quite a lot of infiltration into the ground that's feeding a low-lying aquifer or something like that. And if we pave over the site, we no longer have that infiltration into the ground. If we can put in some sustainable drainage approaches that allow infiltration where it's possible, we get some benefits in terms of groundwater recharge. And anywhere where we put vegetation, rather than take the water away quickly or have some water on the surface, we have the potential for evapotranspiration as well. This can help not only in terms of not having to deal with as much water, but in terms of having a cooling effect. So we're seeing some cities look at the benefit of having green approaches in sustainable drainage that are actually helping to cool the cities down, because the more vegetation, the more evapotranspiration we have, the cooler the air is, rather than seeing our cities as hotspots. So you can see it's sort of endless in terms of the extra benefits we can get by not just putting our water in a pipe and a tank underground, but actually bringing it to the surface and taking a sustainable approach. However, it's not always possible to get all of these benefits from every single design or from every single type of sustainable drainage. So maybe infiltration or water reuse isn't possible because it's flat and the soil isn't suitable for infiltrating into. But with a rain garden or a green roof, you can add some additional value in terms of amenity, water treatment and biodiversity. So we're not trying to say there's a one-size-fits-all approach, but we can combine these different methods and try and take the most sustainable approach for our site. Another example is perhaps some porous paving, maybe even with an underground tank such as this one, which I'll come back to later, which might be able to provide some water reuse and infiltration opportunities by storing the water and using it for non-potable needs, and allowing infiltration out the base. But that's obviously not going to provide much amenity value. And so we have to consider the exact site conditions, the client needs, how much space they can perhaps make available to sustainable drainage. With XP drainage, as you'll see later, we can cover the different hydraulic analysis and the hydrological approach that's needed to adopt these different types of sustainable drainage, and the connecting pipe work as well. So what does our sustainable drainage design criteria look like? This is just an example of perhaps some of the more holistic design criteria. So maintaining pre-developed hydrologic conditions is pretty important. If we can have the layout driven from natural drainage flow paths, that's going to really help us take a more sustainable approach. It's going to be easier to fit these things into the site if we're not working against the existing layout. If we can minimize the amount of earth we're moving around as well, it's going to be a more cost-effective design. And if we can eliminate or minimize curbs and gutters and put in some more vegetation, have the water on the surface, then that's going to help the sustainability of the approach. But we still have the hydrologic and hydraulic conditions that we have to meet. We still have to show that, for example, we're not increasing the risk of flooding, that we're not transferring any issues downstream, and dealing with the quantity side of drainage design appropriately. So our developed flows typically cannot exceed our pre-developed rates, or in some cases volumes, and this might be for a range of different return periods or average recurrence intervals. For example, a 1 year, 30 year and 100 year plus climate change event. We may also have a water quality event. So whilst it is possible to analyse the water quality aspects from a pollution point of view in XP drainage and in our sustainable drainage designs, there is also a water quantity approach to doing this, which is to say, if we were to capture just what's termed the first flush of rainfall, say equivalent to 25 millimetres, typically that is going to contain the highest concentration of pollutants. If you think of a road after a dry period, when it's been quite sunny, there'll have been lots of pollutants left on the road, and they won't have been frequently washed away. So that first flush or first little bit of rainfall is going to have quite a high concentration of pollutants as it washes the debris and the different chemicals off the road. If we capture that, if we keep that within our sustainable drainage system, deal with it in filter media, have porous paving, for example, have some infiltration into the ground, provide vegetation and microbes that are going to break down those pollutants. If we don't discharge any of that water, then actually we've probably done a good job of dealing with the water quality, dealing with the pollutants. So that's just an approach that is taken in some parts of the world as a quantity method or hydraulic analysis rather than tracking individual pollutants. So when we're matching these flows, doing our analysis, there may also be different conditions for the different return periods or different average recurrence intervals. So it's not uncommon to have a requirement that we have no surcharging in our pipe network for a 1 to 2 year event. If we're talking about a sustainable drainage system, that might be more important for our some of our different types of sustainable drainage, in terms of not having too much erosion. So we want to keep the low flows for a 1 to 2 year event and not have them above a certain amount, so we don't get scour and damage to these systems. Then typically we may have no flooding for a 30-year event. So we have a reasonable amount of storage, containment of water within the site, whether that's above ground in a detention basin or below ground in a tank. And then often we have to look at a more extreme event, such as the 100-year event, and sometimes even considering additional climate change factors, such as an increase in the rainfall, and manage the exceedance. So it might be acceptable to say there will be some water that is not contained within our drainage network for the 100-year event, but we have done some analysis and we know how much water that is and where it'll go, and we can actually demonstrate that it doesn't cause any risk to property, for example. So what does this approach look like? I've taken a couple of extracts from the Georgia Stormwater Management Manual, and just to compare how we might see this on a typical housing development. So if we look on the left-hand side, typically we see lots of houses. We're perhaps not preserving any traditional drainage. It gets buried. We might have one drainage solution at the very downstream end, much less tree cover than before. But this is still very common, and in traditional drainage design, the drainage would perhaps not be considered as part of the landscaping or the planning of the site. If we look on the right-hand side, we can see that there is some natural drainage. So we're looking at the existing site and seeing how can we work with those natural flow paths. Actually, if we preserve this, and we can still have some downstream storage capacity in a pond, for example. We can have more landscaping and maybe include some sustainable drainage approaches in our landscaping, have some swales along the edges of the roads instead of curbs and gutters, keep more vegetation on the site. From an amenity point of view and an open space point of view, this is going to be much more attractive. And although it can initially seem quite difficult to justify taking this approach, actually there's evidence to show that having the increased amenity value can add value to a site, which easily justifies adopting a sustainable drainage approach. Slightly different example here, again from the Georgia Stormwater Management Manual. A more commercial development, again, we might completely regrade the site, have lots of parking all in one place, move vegetation around, have to do lots more planting. Or on the right hand side, if we take a low impact development approach, we can keep some of the existing vegetation. We can perhaps use permeable paving on the parking areas, fit in around the natural terrain and slopes on the site. We don't necessarily have to use the whole site for porous paving, but there's opportunities even on a commercial site to include some sustainable drainage. So different types of SuDS when we're talking about, so I'm using the SuDS abbreviation here, Sustainable Drainage Systems, and I'm talking about these individual structures. What are we talking about? There's lots of different ones, as you can see. I'm going to run through a few of these, but there are other terms. Filter strips, for example, is another term used. If we go into the bioretention areas or rain gardens, these are sometimes called biofiltration areas. They're sometimes called biocells or vegetated bioretentions. If we use them in streets, they might have a slightly different name as well, but they're usually vegetated, very, very often vegetated. Depression, normally with some kind of ponding area on the top that's going to collect the water, but the vegetation will help to treat the runoff, and typically we might have sand and washed gravel underneath that also adds additional pollution removal. They're highly customizable, so what you'll find is, depending on the local conditions, what materials available, but also natural vegetation in the area. There may be local requirements that you have to meet, but that makes it all the more important to properly represent them hydraulically, because if we have a different grading of material, we're going to provide a different amount of storage. We're going to provide perhaps a different time of travel through these systems. So we have to make sure we're representing them properly. As I showed earlier, these can be small replacements for inlets or grates. They're normally called rain gardens in that situation, so that we can green our streets, essentially, make them look a lot nicer. But you can use these on any surface. They can be used to take roof runoff, paved runoff, and they're typically considered the best pollution removal device because they have the combination of vegetation and filter media all in one system. Few design considerations, as I said, the flow through that media, how long it takes. We might also want to have a very low flow or high flow outlet. In particular, if we were to get a lot of water, say, rushing into one of these systems because of the sand and filter media, we might get a lot of scour. So we might have a high flow bypass for this, so that the water, in an extreme event, it's probably not as useful, say, for a flooding application. The soil capacity itself, how much water that can hold, and the slope, we would need to consider from a hydraulic design point of view, and in terms of stability. And as I said, the inlets, we need to consider the flows, and as well as the outlets. So we may be draining these with an under drain, but we might also have a high flow weir or a collection pipe that allows water to directly discharge to the downstream sewer. It's important to think about how these systems are treated during construction as well. We often need to communicate what the purpose of this system is, that it's not just perhaps for amenity, and therefore we have to potentially protect it from extra sediment during the construction process. There's various guidance all over the world, but these can be used if we're just looking at treating flows. They're often sized to roughly between 2 and 4% of the impermeable area on a development. And there's lots of great examples of attractive rain gardens. Moving on to swales and trenches. So these are normally channels, often vegetated, although it might be that the vegetation is just purely grass. And generally they convey runoff as well as providing some storage capacity. Very popular next to highways. You get some immediate treatment benefits of having highway runoff go over a vegetated landscape. But they can also be used with a trench underneath. It's normally called a dry swale when it has a trench underneath, often stone filled, and this prevents water sitting on the surface. Obviously we have to be careful in some places not to have standing water. We might get mosquitoes, and it also might be damaging for certain types of vegetation. So it very much depends on the setup. But also having a trench underneath can help to provide some storage capacity. When we're designing these though, we really need to think about that storage capacity versus slope. So on the green side might be what we imagine our storage capacity to be, just based on the dimensions, but actually obviously if we don't properly analyze this from a hydraulic point of view, we might not see that what's happening is the water is actually obviously finding a flat surface, and we've got a lot of unused capacity that potentially is okay, but we need to be aware of. We could consider in this sort of example putting in several check dams to hold the water back to utilize more of the facility or allow more treatment through the vegetation. We'd also need to consider the space. They are going to widen the roads, but if we can adopt them in a way that they provide an amenity value, potentially this is acceptable. And maintenance schedules are quite important for these type of structures. With a swale, if it was grassed, as a lot of them are, you need to be able to mow the sides, so we can't make these things so steep that a man can't walk along it with their lawnmower. Ponds and wetlands is another example of sustainable drainage. And these are typically depressions, I guess to describe them broadly, that collect and store and mitigate runoff. They can be wet or dry if we think just about ponds, so that they provide either a retention or detention facility. Wet ponds will provide more amenity value typically in terms of how they look when it's not, when we haven't got rainfall, we're not dealing with stormwater, and can have different vegetation, perhaps different ecology or biodiversity applications, particularly if we go as far as making it a wetland. But a dry pond might be more appropriate or more beneficial in some cases, so that we can have multi-use a multi-use facility, for example, on a housing development. Maybe there's a communal space, sports pitch or something like that, that can be used in extreme events as a detention basin. So we will probably want to know whether it's going to be wet or dry, and take that into account when we're building our drainage design. They can be almost any shape, have a huge range of different outlets, very, very flexible, and also can provide not just water quality benefits, but flood protection as well, because typically they're designed such that they can take high flows of water, even if that needs an additional sedimentation bay. Or if it's already got water in, we can have extra capacity in the pond to provide flood protection. Another example is underground chambers. Might be not what first comes to mind when we're thinking about sustainable drainage, but actually these types of storage can be used in combination, say, with some kind of surface solutions such as permeable paving. For example, these crates, they look like sort of old-fashioned milk crates, often the plastic systems with lots of crosses in them, but they have a really high void ratio, maybe up to 90 or 95% void ratio, so they provide a lot of storage. They can be wrapped in a membrane that can stop sediment getting in but allow infiltration, or they can be completely sealed so we don't have infiltration. These arch type systems are just another typical approach used, and sometimes what we find is these are used to provide storage for water so that we can reuse it, say in for watering gardens and so on. So they provide lots of storage, not so much on the water quality side. Really useful where space is at a premium. But again, we need to assess them hydraulically in particular to see how they work with flow controls. We'd normally, with something as providing as much storage as this, we'd want to control the flow at the outlet and make sure we're using it to its full capacity. So I mentioned permeable paving might sometimes have these underneath, but they might also have different types of material, gravel type material underneath, to provide some storage, but also to provide some treatment. Can be block paving that isn't filled with sort of fines, so no sand filling all those gaps, or it can be specialist materials like specialist tarmacs and surfaces that will allow water to go through. Getting the water off the surface as quickly as possible is really important, can minimise danger for driving conditions, but also minimise standing water in car parks, which can make them unusable. So lots of applications, private driveways, walkways and parking lots. Again, typically quite important to understand the slope of these. So we don't want to assume that it's completely full if it's actually on a steep slope. It's sometimes assumed that if we have a car park and we want porous paving, that we have to do the whole car park. But actually, we may find that we can provide enough storage or enough treatment capacity just by doing a section of the car park. So that's something to bear in mind as well. Where these are on private driveways, though, we have to think about whether they'll be maintained in the future. So worth considering how that's going to be managed in the long term. There's a question popped up about that, but I will just come back to that at the end, if that's okay. Another example is a green roof. These can actually reduce the total runoff volume into our drainage network. Very effective at low flows. We do get less effect, I guess, as the rainfall gets more extreme. But they have other multiple benefits that they can provide: thermal benefits to the actual property, some insulation benefit, as well as aesthetically looking nice, and sometimes even providing additional outside space in congested urbanized areas. They can be retrofitted sometimes on buildings, but also are popular on new buildings. And especially in cities, it's a really good way to green a city and to potentially reduce the air temperature and make it look nicer. Rainwater harvesting is another example that's perhaps quite small scale at the property or building level. And this is where we're talking about having some storage tanks that will reduce the total runoff volume. Sometimes these are used just to store water for reuse, but they can actually provide additional detention storage. So if we're putting in a tank, we may have an overflow, for example, halfway up the tank, which means the top of the tank is always available if there's an extreme event to come along, but we can water gardens, flush toilets, do washing, that sort of thing. And again, can be retrofitted or put on existing buildings. There are various schemes and codes that will sometimes promote this in new development, particularly in water-stressed areas, such as Australia, where drought is fairly common, and actually being able to store some water and use it at a property level is really important. The antecedent conditions can be important. So have we just had a very wet spell or a very dry spell? And that can be something to consider in the hydraulic modelling in terms of, do we want to assume that this is full before we start, or can we take some averaging and say that, well, no, actually we don't want to assume it's all full, maybe we assume it's half full, and so on. So just something to bear in mind. If you were to run some continuous simulation, then we would obviously take that into account. So then proprietary devices. So there's also lots of other manufactured stormwater facilities. This is just one example here, a Hydro International downstream defender. So this is specifically designed to provide some water quality treatment, can remove some of the pollution, sediment and so on, particles from the water before it's discharged into a water body that needs protecting, say for example a downstream river or lake. They tend to be treatment focused and pollution removal focused, but it's just another part of a sustainable drainage approach. So I've spoken about a lot of different sustainable drainage systems. I haven't covered everything. We haven't talked about soakaways, but we also need to consider how these are connected up, the pipes and channels, and properly represent them in terms of the hydraulics, so we can see the impact on them on each other. It's especially important when the system is distributed around the site, because we don't want to necessarily assume they're all empty at the same time or all full at the same time. So to summarize, we need some analysis. Also need to consider which ones have ponding area, what type of filters, the outlets, and ideally have customizable facility configuration. So I'll spend a little bit of time now looking at XP drainage and how we can take into account the storage, the infiltration, and produce something that's easy to report and communicate at the end of it. Little introduction to XP drainage. It's purpose-built drainage design and review software for optimized sizing, analysis and visualization of source measures and traditional stormwater infrastructure. So these images that I've shown throughout the presentation, permeable paving, bioretention, swales, for example, these come from the XP drainage software, and these are to help you understand what sort of parameters you need to put in to design these. I will switch to the software now and spend 10 minutes in the software and then come back and look at some of your questions. So I'll close this down. Here we've got a very simple little design, just 2 sustainable drainage systems in here, but we could have many more connected up. But I wanted to show you specifically on the rain garden that some of the details that we can include in XP drainage. So we've got a catchment area here in green, which is draining, is connected up here into our rain garden. And we've got a second catchment area just here, which is draining straight to the pond. The rain garden itself, this dash line shows that when the water comes into the inlet, we've set up a bypass. So in a very extreme event, we don't want too much flow going into our rain garden, and it's actually going to bypass the rain garden and connect into the downstream manhole. We've got 2 outlets from our rain garden. One is the under drain itself, and one is a high flow weir, also connecting downstream. And then these all go down to a dry pond at the end of our system. So if we open up the rain garden, we can see we have the dimensions that we put in here. We can allow for the slope. At the moment we're assuming no slope. We may want to update that. But this little image helps us match up what does our exceedance level mean. It's right at the top. When we talk about slope and side slope, what are we talking about? On the filtration layers tab, we can see that we've got 2 different filter layers, and our void ratio and filtration rate is accounted for. So that means when we're reporting how much water's been stored, we're taking into account quite a lot of complexity in this bioretention area. And we're also taking into account how long it takes the water to travel through this. So some filter media might be very slow. Having lots of vegetation might slow down the flow, and that's going to have an impact on our downstream water level, and potentially on how much storage we need to provide across the whole network. Our outlets, as I mentioned, we've got our under drain and a overflow weir. On the inlet side of things, we have just a high bypass rate. So anything over 15 litres per second is going to bypass the bioretention system. But there's several other methods of restriction we could use, including the HEC 22 manual, which is quite widely used both in the United States and around the world for describing inlet capacity. So that's some of the detail we can put in. We can see this bypass. If we just have a look now at the profile again, and I'll just make this a bit bigger, we can see that it's not just in terms of what we specify, but actually in terms of the analysis and the reporting that we get quite a lot of details back. So what happens is our water comes into this network. Initially, the filtration rate isn't restricting the flow, but as the water builds up, we actually get 2 water levels reported both in the base and in the top of our bioretention area. So those different filter layers and the under drain can be seen, as can our different outlets. And it's mostly traveling through our under drain downstream to our pond at the end of our system. We could also look at the bypass route, or if we actually go into the details of the results for our bioretention area, we get lots of graphs showing us the total inflow and outflow and so on. But we can actually see, if we just look at, for example, our bypass there, we can see how much flow is going through our bypass both graphically and in detailed on the results. So we can show our component inflows. The continuation flow goes through the bioretention area, and until we reach 15 litres per second, no bypass, then our bypass kicks in and we get the additional higher flows, which would potentially damage our bioretention system going down the bypass. So quite a lot of detail available if we need it. We can also view it in 3D if we want to, and just see those different water levels fill up, exaggerate the y-axis so we can see our underdrain here, our different filtration levels, and see the water level rising in the ponding area at the top. On the overall results, as well as looking at these structures individually, we have a summary. So we can see that at the moment, they're not used to full capacity, which we could see on the profile. And they're both status is okay. We've got 600 meters cubed of lost volume, which is infiltrating from our pond, and 50 litres per second is our maximum outflow off the site. Because this is the most downstream system, that's the maximum flow off the site. So we probably want to see whether that's acceptable comparing to our existing condition. I've actually got several different phases within the design, including an existing option within which we just have pre-development runoff occurring. And if we go to the results and look at our phases report, we can actually compare the results of the two different phases. So our maximum outflow from our existing condition is actually only 30 litres per second. So quite easy for us to produce reports, see quickly whether we need to make any changes. That suggests we need to restrict the flow more, potentially making the pond bigger. So I won't go into that now. I just wanted to give you an introduction. I can see quite a few questions come in, so I want to take a bit of time going through those and making sure you get that password so you can get your certificates for attending. Okay, so the first question is, how sustainable drainage systems affect the right-of-way, road slope, corridor width, maintenance and safety requirements for new developments? Well, all very good points, all good questions, and something that is going to be different on every single site. It's definitely something that I would recommend early discussion about with the local approving authority, with your client. They have been implemented in lots of public roads and private roads around the world. I'd say in terms of right of way, it doesn't usually provide a problem walking on, say, I think this is specifically in relation to permeable surfaces. It doesn't usually provide a problem other than maybe for maintenance periods, but that's quite infrequent for permeable paving. Slope, in terms of slope, I'd say that it's more likely the road slope will affect the drainage system than the other way around. And maintenance and safety, they have to be considerations in the design. So I can't really give any specific advice on those because it's going to really vary per design. Next question is XP drainage compatible with InfoWorks ICM? And does it have the same SuDS modelling capabilities? So no, these are two different products for two different jobs. XP drainage is focused on design, talking about smaller scale design developments. ICM would be much more a modelling product. I mean, the range of applications you can use InfoWorks ICM for is huge in terms of storm and sewer applications, and the SuDS representation is therefore difficult. We can't go into or it wouldn't be practical to build a model with thousands of nodes with the level of detail XP drainage has. In the same way, we wouldn't use XP drainage to represent thousands and thousands of nodes in a whole system. So they do quite different jobs. We can transfer information from XP drainage using CSV files. In the future, we are working to develop that link. You may not know, but XP Drainage was a product by a company that merged with Innovyze last year, XP Solutions. So we are still working together to get those programs more compatible, but there is a way to transfer data using CSV files and GIS files currently. So a couple of other questions on ICM, which I think I've answered. If there's any other follow-up, I will get back to you, or you can contact me again. I'll put my email up at the end. How to deal with green roofs or design green roofs. So green roofs can be represented. There's a few different ways, actually. Lots of our customers do them as bioretention systems, with the grassy or vegetation bit on top as the ponding area, and the using a layer of the filter of the bioretention area to represent the green roof. But I'd be very happy to talk more with the person that asked that question. Can SuDS deal with a combined flooding manhole or just a stormwater one? SuDS can deal with combined flooding manhole, but I'd say the design would need to be quite careful. There are some vegetation types that can deal with not just stormwater but combined flooding water. I think we're talking about like combined sewer overflows here. For example, reed beds are often used to treat that type of sewage. I would say typically we're just talking about stormwater contributing to these types of system, but I wouldn't rule it out. I would just say there would need to be some careful design considerations, and it would probably, probably be something that you'd not just want to do without thinking it. Okay, questions have slowed down. Can we just one more about green roofs there? Converting an existing roof to a green roof. So I mentioned modelling the green roof as a bioretention area, which would be representing it as part of the hydraulic model. There is also the option, rather than having runoff, the hydrology, if you like, runoff from the roof, to change the hydrograph before it gets into the network. So we don't necessarily have to model all the details of the layers, but there's an option to have a green roof type of catchment area, if you like. Somebody's asking a question about comparing between traditional and SuDS solutions. So yes, with the phases, you saw we were comparing an existing development with our post-developed site, our completed design. We could have different phases to represent, say, an approach that used just pipes and manholes and storage tanks with a sustainable drainage solution, and we could look at the water quantity and the water quality and compare those two different phases. Somebody also asked about weir height and width, which can be changed. Yes. It's coming up to the hour, so I'm going to show the password, and I will contact any other outstanding questions, or you're welcome to get in touch with me if you would like to. But I wanted to put my email address up there, jessica.jefferys@innovyze.com, if you have any follow-up questions. As I said, I'm the product manager for XP Drainage. So thank you for joining us today. I think that's all that's left to say. Thank you for giving up some time to listen to our webinar. Hopefully it's been useful and a good introduction to sustainable drainage systems.